I'm going to explain about conservation of angular momentum. As we know, every object that moves has momentum. If we consider a general shape of a body rotates about a fixed axis with a constant angular velocity omega, each particle in the body has linear velocity v and hence has linear momentum p is equal to mv. But at the same time, it has angular momentum since the body is rotating. Angular momentum, which is L, is defined as r cross p, which is r is the perpendicular radial distance of each particle from the axis of rotation and p is equal to momentum. Angular momentum is a vector quantity and the direction of angular momentum is same with the direction of velocity. From the formula to get the magnitude of angular momentum, L is equal to Rp sine theta. P is momentum, which is we know is equal to mv. So substitute P equal to mv into the equation, we get L equal to Rmv sine theta. In rotational motion, R and V is always perpendicular to each other. So hence, theta is 90 degree. So sine 90 degree will equal to 1. So L will equal to mvr. Substitute V is equal to R omega into the equation. We will get mr omega r and simplify to get mr squared omega. For rigid body that rotates, the sum of angular momentum L is equal to the sum of mr squared omega. And we know mr squared is equal to I. I is moment inertia, which is a property of an object to resist any rotational motion, and it depends on its mass and distribution of mass about the axis of rotation. Next, I will explain about principle of conservation of angular momentum. In linear motion, when there is no external force, momentum is constant. Similarly, in rotational motion, when no external torque acts on a system, the total angular momentum of the system about any axis of rotation is constant, which is L equal to I omega equal to constant. From here, principle of conservation of angular momentum state that angular momentum initial will be equal to angular momentum final. The example for this principle is the ice skating. The ice skater starting to spin with her arms stretched. She increased her rotational speed omega by bringing her arms close to the axis of rotation, which is her body. This caused her motion of inertia I to decrease. As I omega equal to constant, when I decrease, the angular velocity omega will increase. Watch this video together. We can see that the ice skater rotates faster when her arms is close to her body. Here I want to show one example for calculation. The question is, a horizontal disc rotates about an axis which passes vertically through the center of the disc with angular velocity of 100 rpm. A small particle of mass 10 gram is dropped onto the disc 9 cm from the axis and it sticks to the disc. If the angular velocity is reduced to 90 rpm, determine the moment inertia of the disc about the axis. So here we have the initial situation and the final situation. Given from the question is the angular velocity, omega naught for initial, omega for final. We have to convert the omega naught from RPM to radian per second by times 2 pi over 60. So we get the value for omega naught and omega in radian per second. After get the value, we can use the principle of conservation of angular momentum, which is L initial equal to L final, and L is equal to I omega naught for initial, and for final it would be I ds plus I particle since it's moved together with common angular velocity omega. We substitute I particle as mr squared. Substitute all the value that we get from the question and we will get the IDs is equal to 7.3 times power of -4 kilogram meter squared. You can try other exercise to understand more. That's all for now. Thank you.